So let's start talking about psychrometric application. So we last time we talked about the mixture of different gases and how we can come up with their properties like the mixture molecular weight or the mixture enthalpy or the mixture specific heat. So now we'll talk about one particular mixture. That's a mixture of dry air and water vapor. Okay, so dry air is our air, the O2 and N2 and whatever traces of molecules we have in our air. And of course, sometime, especially in the summer, we have a lot of water vapor in the air. So that's called moist air when you have dry air and water vapor. So that's what we are interested in. And that study of water vapor and dry air or moist air is basically called psychrometrics, right? And as you will know today, it's very important for HVAC application, for indoor air quality. If you want to make the people feel happy in their workplace or their homes, you need to adjust not only the temperature. It's not all about just like let's cool it and heat the air, but also the water content. The water vapor content is very important to make them happy, right? If it's too dry or too humid, people will not really be happy, as well as a lot of industrial processes that also require not only the temperature control but also the humidity control. Because it controls a lot of things like evaporation and drying and all those industrial processes, as well as in libraries and museums. So moisture content is very important, right? So the air, dry air, and water vapor both will make this new mixture called moist air. And like we said last time, they could have two different pressure, partial pressure. The dry air has its own pressure, the water vapor has its own pressure, and then together they make the mixture pressure. So when in the room where you are sitting right now, when I ask you what is the pressure, and you say it's 1 atmosphere, 101,325 Pascal, well, that is the mixture pressure. Part of this is dry air and part of this is water vapor, right? So they can have two different pressure. They share uh, the room, so they will have two different pressure. The total is the mixture pressure, but they can't have different what? They cannot have different temperature, right? As long as they are in the same room, they will have to have the same temperature. Okay? They split the pressure. You get 10%, I get 90%, depending on our what? Mole fraction, right? Last time we said that the partial pressure is the mole fraction multiplied by the mixture pressure, right? But they so they can have different pressure, but they cannot have different temperature. And again, why is that? When you study the gas kinetic later, when you go to grad school, you will realize that the temperature, when we say that air is hot or that air is cold, that air temperature is 100 degree and that air temperature is 80 degree, that temperature is nothing but a number that tells us how quickly they are moving in the room. It's a measure of kinetic energy that we are experiencing in front of us. So the more energy they have, we say the higher their temperature is. All right? And it's really fascinating when you go to grad school, you realize that the temperature is just a parameter that we put on top of a Boltzmann distribution, Maxwell Boltzmann distribution, to say how quickly they are moving. All right? So they have the same temperature, but they could have two different pressure depending on how many moles are in that room. Partial pressure will end up being the mole fraction multiplied by the total mixture pressure, right? So let's go to this chapter 12 and see what else he offered to give us. So I have to go flip my face every time. All right. So one nice simplification is he's saying that usually when in our air, in indoor air application, usually the water vapor is not really that much. The mass of water vapor is very little compared to the mass of the air. Okay, so we are not gonna have a mixture of like 50% water vapor and 50% dry air. That wouldn't happen. You will see how the the amount of mass of the water vapor in the air is not gonna be that much. All right. So This will make our life a little bit easier, right? This is the place where he say, now we will have dry air, we have water vapor, and let's call the partial pressure of the air, the dry air, P air, and the partial pressure of the water vapor, B P B V, right? And what is P without any subscript? That is the mixture pressure. So at room, in the room where you are, when you are sitting right now, that pressure is, that P is 101,325 for atmospheric pressure, right? Very good. And those are the mole fraction, and therefore you can recover the partial pressure of the two of them, all right? So this is important thing to realize right now, that the partial pressure is a kind of the other side of the coin of the mole fraction. So knowing the partial pressure is knowing the mole fraction. Knowing the mole fraction is knowing the partial pressure. Right? So now the total pressure of the mixture would be, let's add the two of them, B air and B vapor. So this is the TS diagram of water, right? Not of the air. This is the TS diagram of the water vapor. And this is the room temperature, or the mixture temperature. We got air, and right now in your room, hopefully the temperature is around 75 degree Fahrenheit. So this is their temperature. It's the mixture temperature, and as we said, it's also the vapor temperature and the dry air temperature. They all have the same temperature. And here is the B vapor. This is the partial pressure of the water vapor. This is how much he share out of the 100, 101,325 Pascal. This is how much is B vapor. All right. So he's saying that the air, for the air temperature and pressure that we experience in usually our buildings, the water vapor would be over here. It will not be there. It will be over here. If it was here, if the water vapor is sitting over here, what is that? Remember the TS diagram? So this is saturated liquid, this is saturated vapor, right? Like if I ask you to calculate the H here, you'll go to the steam table and get H, what? Hg. And here you will get Hf, right? So that is saturated vapor, right? So he said that for most application, the vapor pressure will be sitting over here. So it is usually superheated vapor, right? And of course, when you hear superheated, you think, that's like 600 degree Fahrenheit, and like in a in a boiler or something that generates steam for a turbine that run the city. That is what you think of superheating. But this is all superheating. Anything in this region is superheating. So that is superheating at 70 degree Fahrenheit, right? Why superheated? Because he's far away from his saturated condition at the same temperature, right? So basically he has very low pressure, right? Compared to B saturation at that temperature. That's why we call him superheated. Very good. So now if we are here, we would be saturated vapor, right? The air will have water vapor that is saturated vapor. Does this mean that all what, if we are here, then everything is water vapor, will be basically breathing water vapor? No, right? No, there is still dry air. It's just that the water vapor in the air will be sitting over here. He will be sitting at his saturated pressure, right? Here he's superheated and have lower pressure than B saturation. If you increase the pressure, and how you increase the pressure? Free quiz. Remember what I said 2 slides before? This by increasing the mole fraction, right? Having higher mole fraction mean having higher pressure. So if the mole fraction of the water vapor in the mixture is small, you will be here. If you start increasing the mole fraction, you may end up being here, right? So the ratio of what is the partial pressure of the water vapor in the air, whether you are here and you have very small partial pressure, or whether you are here and you have very high partial pressure at mixture temperature, right? The ratio between those two pressures is the relative humidity phi. So that is the first parameter that we would use in this chapter related to psychrometric. Okay, so B vapor over BG at that temperature. And what is that P? That's the mixture pressure. He's saying that they are all basically, whether you are here or here, you are still sitting at room temperature, and this or this is part of the big pressure, right? The big 101,325 Pascal, the big 1 atmosphere. Okay, it's just that here you have little share of that pressure, here you increase your share. All right? And so if that phi is 100%, that means that the water vapor is saturated, and we'll see what this means later. But basically, this is how much he can take as water vapor. He cannot increase the mixture after that. Imagine if you start increasing the mixture, the mole fraction of water vapor up beyond this point, what will happen? He will end up, you're still increasing his pressure, right? We said the pressure is the mole fraction. So if you add more molecules of water vapor and you want to go to like high pressure like this, what will happen? You will end up meeting the temperature over here. So basically the water will start becoming liquid. It will not be vapor anymore. He will start making cloud in the, this will be fog basically, right? You will end up putting too much vapor that he cannot take it anymore. He cannot sustain the water vapor in the form of vapor, right? So 100%, that is saturated air. And 0%, if phi is 0, that means that you have only dry air, no water vapor whatsoever. Okay? So if you dropped all the water vapor, I'm saying this, if you dropped all the water vapor in the mixture, no more water vapor, only dry air, the phi would be 0. Because it would be what? 0 over Bg, right? That is dry air. Totally dry air. Alright. So the pressure B vapor over B gas at the same temperature was the humidity, relative humidity. Alright? Was relative humidity, phi. There is a humidity ratio, and this symbol is omega. Okay? But in the book, sometimes they write it W. So be careful whether it's W written as W or omega. Anyway, the humidity ratio is the mass of the vapor over the mass of the air. The relative humidity was not the pressure of the vapor of the pressure of the dry air. It was the pressure of the vapor over the pressure of the vapor if it was saturated at room temperature. But the humidity ratio, omega or W in other books, it's the mass of the vapor over the mass of the dry air. So what is the unit of this? It will be kilogram water vapor over kilogram of dry air, right? So MA is not the mixture mass. MA is just the dry air mass. All right? Very good. So he will tell me, he's saying over here that since we said that there's usually very little water vapor in our air, you know, the air inside houses and factories and stuff, since this mass is very small compared to this mass, expect the humidity ratio to be very small numbers, right? So when we start getting those numbers, calculate the humidity ratio, you will see that the number will be small numbers. Okay, we are talking about 0.001 and things of that order of magnitude. Okay, so now he will try in the next line over here to come up with a way to calculate omega from phi. What is phi? Relative humidity. So he will try to calculate humidity ratio from the relative humidity. The relative humidity was basically pressure. right? So how we can get a relation between this and pressure? Well, the mass, where did we see the mass in any other equation? And if you have been looking over here, it is the equation of state, right? Remember PV equal MRT? PV equal MRT. So M would be PV over RT, right? And that's what you're looking at. So the water vapor is again superheated most of the time. And so since it's superheated, then we will just treat it as a gas. And so since it's a gas, then B vapor, V vapor, okay, PV equal MRT. So therefore the M is PV over RT. So what is that? That's R universal. So the R for a gas, for example, R here is 287, right? And R for other things, we open a table and find out what's the gas constant and what's the unit for R. Joule per kilogram Kelvin. This is not R. This is R bar, and some books write it R sub U, R universal. And this R universal divided by M, the molecular weight, is R. So he is removing R, and instead he is writing R universal over M, which is the same thing, right? So at the end of the day, this M air, again, the air is ideal gas, so also the air, if you want to calculate the mass of the air, you would see PV over RT, that is the mass of the air. And instead of R, you write R universal over molecular weight of the air. And the same thing for the water vapor. Okay, the reason why you did this is because you want to cancel the R with the R and the T over the T. Again, as I said earlier at the beginning, they have to share the same temperature. If they are sitting in the same room and they are bouncing against each other, if one of them is moving faster than the other one, he will accelerate him, right? So they cannot really survive in the same room with two different temperatures, right? Because of the constant collision, they will basically push each other, right? It's like in your research group, if you have like two good students and two lazy students, at the end of the year, the two good students either become lazy or the two lazy students either become good, because this constant interaction between each other will end up basically making you coalesce to the same productivity. Hopefully it's up, right? Not down. So they have to have the same temperature. So the T cancel with the T, the R cancel with the R, the volume cancel with the volume. And what do I have left? The mass or molecular weight of the vapor, P vapor, over the molecular weight of the air over P air. And again, the air, when I say air, I mean dry air, right? So dry air, what is dry air? That's O2 and N2 and bunch of like very little helium and argon and those inert gases. At the end, the molecular weight of our air on Earth is 28.97. Okay? 28.97. It's because it's not all nitrogen and it's not all oxygen. That's why you end up with this. Right? Very good. And for the water vapor, H2O, what's the molecular weight of H2O? H2O, so 2H and 1O, so that's the 18, and 18.02 because of all the isotopes and stuff. So now, so actually we can supply this number, divide, it's 0.622, and you got yourself your second equation in this chapter related to psychrometric. I mean, we had some equation when we talked about that last week. So we have one equation for relative humidity, and now we have an equation for humidity ratio. And the omega is 0.622 B vapor over, he removed B air, the dry air, and he wrote B mixture minus B vapor, right? Because of course B air is B mixture minus B vapor. So now if you know B vapor, you will be able to calculate omega, since that is like known number, atmospheric pressure, if we are on the surface of the earth, 101,325. So then how do I get B vapor? The relative humidity. So if you know phi, you'll be able to calculate B vapor, and once you know this, then you'll be able to calculate omega. So there are a bunch of problems You know, and if you have this in an exam, that will be your luckiest day, because all you want is just to convert the relative humidity to be vapor, and of course you will get this from the steam table at T and V and P. He tell you the relative humidity is 50%. You come and say then B vapor is 50% of this. And then once you have your P vapor, you put it over here and you got yourself your humidity ratio. What's the unit of this guy? Joule, no, kilogram over kilogram. Kilogram water vapor over kilogram of dry air. Right?